Let's imagine these two green balls to be hydrogen atoms in a bond. Notice how they are oscillating about some equilibrium position. I've released them very close to that equilibrium position. This distance of separation is known as the equilibrium bond length. We can imagine one atom held fixed and the other one allowed to move back and forth. I've increased the distance from where I released the atom, and you can see it wildly moving back and forth. Let's make a graph of the forces that contribute to forming this bond. Here's the repulsive force. Here's the attractive force. Notice that these forces are not symmetrical. You find their sum by just adding up the heights. And we get this line. The equilibrium position is right where the total force crosses the x-axis. The potential energy is given by this curve. Notice that the minimum potential energy lines up with the equilibrium position. The potential energy is negative. It rises to 0 when R equals infinity. We can follow the oscillating atom on these curves. If we cool off these atoms, taking away energy, they'll settle down at the equilibrium bond length. That's where the force is a 0, that's the red dot, and the blue dot is at the minimum potential energy. If the atoms have more energy, as they come together, they're going to overshoot the equilibrium position and go into the repulsive force area. As the atoms move apart, they go into the attractive area. Either way they go, the potential energy rises from the equilibrium position. If I add more energy and more energy, notice how much longer the atom spends further away than close in. This is an example of heating the molecule. If we add enough energy, you can see that the atom in the bond separates and slows down, eventually returning. But if I add more energy, it's going to slow down, but it may never come back. Well, eventually you reach a point where the atoms won't come back together again, and you will have broken the bond. Now watch the speed of the atom as it moves apart. Is it increasing or decreasing as it separates? It's just like throwing a ball up from the earth. It's going to slow down. A lot of kids get the impression that when the bond breaks, the atoms go flying apart faster and faster. Well, that doesn't make sense in terms of the attractive force. The attractive force is going to have to slow it down as it goes away. Here we have a model using an invisible spring between the atoms. The equilibrium position is in the middle of the range of this motion. Let's take a look at the total force. It's that straight line that we get from a spring. What about the potential energy? It's at a minimum at the equilibrium position. And you can see by the markers that follow this motion that the minimum potential energy occurs right when we cross the x-axis with the force graph. Now, why is this an incomplete model for a chemical bond? Well, because the force goes on indefinitely, linearly, and that's definitely not what's happening. There's no way you could break this bond because the forces just keep increasing and increasing. Using this spring model for a bond, the motion of the atom is symmetrical. It spends the same amount of time further out and closer in from that equilibrium position. That's a big difference from the way a bond really works. Now, comparing the spring model to the actual quantum mechanical bond model, we can see how much more time the atom spends further away than it does close in. This helps explain why metals expand when they're heated.